Alright, welcome to my first video of my Calc 1 series. Calc 1 has two main parts. There's differential calculus and there's integral calculus. Today we're going to be starting with just basic derivative, which is this word right here. Now, in very simple terms, derivative is just the slope of a function. And we know the slope as just rise over run. We know this from algebra 1. And if you have this line, y equals x, just goes through the origin and goes up. The slope of the line is just the change in y, the rise, divided by the change in x. So we can rewrite this as just change in y over the change in x. That equals the slope. But where calculus comes in is, say we have a different line, and it's like curvy. Well, the slope at this point right here, it tends to go downwards. But right here, it tends to go upwards. It's not constant. So the question is, how do we find out what those slopes are? We can find the average slope. It's just a straight line. The average slope over this area right here is just going to be that secant line. But what if we wanted to find a function that if you plugged in a value for x, you will get the slope at that point, which is what the derivative is used for. But also, notice how I said slope at a point. The derivative is all about instantaneous rate of change. And maybe a little counterintuitive because rate of change implies time, and time can't be instantaneous. There has to be some change in time for you to have something change. So that's where calculus comes in. And what we're going to do is have this little drawing preset. So let's say we have our curved line f of x. I promise this will make a little more sense later. So we have this curved line f of x, and we drew just a random secant line across it. Point 1 here, point 2 here. And we drew a secant line connecting them. Now remember that this line right here is just the average rate of change. But that's not really what we're looking for. So first we have the x-axis here, y-axis here. And here, this first point, we just have f of x. We move over x amount. But then, between point 1 and point 2, we have delta x, a change in x. So it would make sense that at this point, it's just x right here plus delta x. So we have f of x plus delta x. And that's what we want to do is, remember, this is our change in y, this is our change in x. So what we want to do is find the slope. But not quite the slope of a secant line, but actually a slope at a singular point right here. So where calculus comes in is we're going to keep drawing secant lines until we get so close to the single point where we just barely touch it. Barely touch it. And we find this tangent line right here. And the slope of this tangent line is our instantaneous rate of change. This would be how fast your car is going at time equals 3 seconds. If it's accelerating, it will be at a different speed when time equals 4 seconds. But the thing is, as we move these points closer and closer, delta x gets smaller, to the point where we reach a single point, delta x equals 0. There is no change. You can just think of it as the 2 points are moving closer and closer until they're right on top of each other. So let's first let's define the derivative. So we have this fancy symbol here, like limit as delta x approaches 0. And, well, derivative's just a slope, delta y over delta x. So let's just think about this. We have this point right here minus this point right here. So let's just do f of x plus delta x minus f of x all over delta x. So what does this thing mean right here? Because this is what really defines the derivative. Ignoring the limit, you just have the slope, which is not exactly what the derivative is. It's close, but not quite. When the delta x, the change in x, approaches 0, where these points get so close together that they just end up on top of each other, that's the derivative. And how are we going to evaluate this limit? Well, it's a little easier if we do an example. So let's have f of x, and let's just say it's just a parabola. We can get, and we'll keep it. And we'll draw just a parabola down here. So let's have f of x equals x squared. So I should also write, this is the derivative. This is your fundamental definition of the derivative. So if we want to find the derivative of x squared, well, we need to find out what f of x plus delta x equals, what f of x equals, what delta x is. Well, f of x is just x squared, so we know that. But what does it mean to have f of x plus delta x? Well, it's just, instead of just a regular x right here, where you just plug in this value for x into the function and you get a y value, now x is actually just x plus delta x. So there's a little more juice that goes into it. So instead of here, now you get here. And delta x is big, maybe you're like way up here, or you're just down here if delta x is small. So what we want to do is just redefine x as x equals x plus delta x. So let's write that. X equals x plus delta x. And we're just going to plug that into the function. So f of x, f of x plus delta x equals x plus delta x, quantity squared. Remember that. And we also need to FOIL. So this will also equal x plus delta x times x plus delta x. And we're going to FOIL. So like first, outside, inside, last. So we get x squared plus 2x delta x plus delta x squared. And this equals f of x plus delta x. Hopefully that made sense. It got a little messy towards the end. So now we know what f of x equals. It's just x squared. We know what f of x plus delta x equals. It's this right here. And then delta x is just the change in x. And this is what we're evaluating as what happens to the slope as this change in x approaches 0. So let's move on and let's get rid of this. Just delete that. And so the limit of delta x approaches 0, we found that this equals x squared plus 2x delta x plus delta x squared minus x squared, because I should write that. F of x is just x squared. But this is also all over x squared. But one thing I realize is this is a positive x squared, this is a negative x squared. So these actually cancel. And here's like a pro tip. If you do this and things aren't canceling, you probably did something wrong. But that's not all the canceling we can do. We have an delta x here and two delta x's here, delta x squared. So we can actually cancel these out. And instead of delta x squared, we just have 1 delta x. So let's rewrite this. We just have 2x right here plus delta x. We only have 1 left over right there. So we are really close to what our derivative is. But don't forget this part right here. This is the important part. The limit as delta x approaches 0 is 2x plus delta x. And when delta x approaches 0, well, this just goes away. So we're left with 2x. So let's just write this a little more officially. So f of x equals x squared. Now the derivative, and this little prime symbol right here, this little dash, means derivative. So the derivative of f of x equals 2x. What does that mean though? I mean, like, that's cool and all, but it's just another function. What does it mean? So let's also get rid of this. So we have our function x squared, we have x here, y here. So let's just think of x equals 3. We'll say this is 3 right here. Well, if we want to find like what f of x equals when x equals 3, well, we just plug in 3 here. We got 3 squared equals 9. So f of x, or f of 3, equals 9. But what is the slope at that point? What is the instantaneous slope when x equals 3? Well, that's just the tangent line at this point, and the tangent line turns out to always be 2 times x. So we can do 2 times 3 equals 6. So the slope of the line when the instantaneous slope of the line when x equals 3 is 6, while at the position of 9. We're going to do a little more practice with this and look into graphs a little more, but this is our definition of the derivative.